Hello and welcome to this Manufacturing Systems Technology Module 18. We in the last module talked about the different stages of process capability or the process planning with a stage 1 for analysis of part requirement, then obviously stage 2 for the selection of the raw work piece, the stage T for the manufacturing operations and the sequences, and then we are talking about machine tool selection. And in that respect we also mentioned about that whether the process capability of a machine can somehow be incorporated for doing the selections of the machine tool. So let's look at a problem example here where we talk about a small mathematical model for understanding the interactions between the design and the manufacturing process in a turning operation of a cylindrical shaft. Okay, so here we consider a simple product. It's a case study where there is a cylindrical shaft. Okay, and the design stage that is concerned is with specifying tolerances on the shaft. Obviously, the manufacturing stage is essentially a transformation process, changing a bar stock into the finished shaft meeting the tolerance specification on the design, and the transformation process indicating inputs outputs are kind of shown here. So let's say this is the process. Okay, and there is an input to the process which can be in form of a rough bar or a stock or something of a certain dia. There is obviously a transformation throughout this process where it makes the output on the other side, and in the process of doing that it also rejects some material in this particular zone. So some of the material which is to be processed is not really meeting specifications and gets rejected. So the question is whether the machine that we are choosing, or the machine that we would really try to think for the try to select, would have the right process capability so that minimum rejects are possible. That is the whole idea, right? So obviously if you look at the process capability analysis, let's say any process is basically distributed or defined by the so-called normal distribution. So let's say in any machining process there is a certain normal distribution represented by the bell-shaped curve where it talks about a process mean. Obviously the machine would have a mean value mu, so this is the process mean. Okay, and then there is a so-called process standard deviation which as we probably all know that if you go to mu plus minus 3 sigma, it covers more or less about 99% of the parts of the whole distribution. So the question is again, what is sigma, what is the spread of the process, what is the variability of the output of the machine, and that's what is meant by process capability. So in this particular case, let's say there is a situation where we have a tolerance value given by the drawing. Okay, let's just eliminate this mu plus minus 3 sigma. Okay, because that's as I told you or described earlier, it's a process capability issue. So here let's say the tolerance values which come by the design have a upper tolerance limit and a lower tolerance limit. Let's say we have read a design and we figure out that the shaft is about 1 inch in diameter and the tolerance value that is allowed by the design is plus minus 0.008 inches. Okay, obviously the upper limit then would be 1.008 inches and the lower limit would be something like 0.992 inches, and that's how the shafts would vary. That's how the shafts would be accepted or rejected. So anywhere below the lower tolerance limit or above the upper tolerance limit are the rejects. So you have this area which shows the rejects because of the shafts not meeting the upper tolerance limit, and this is the area which shows rejects because of the shafts not meeting the lower tolerance limit. Okay, so having this kind of a situation, now the question is, to this process can we actually match this capability and try to figure out what would be a good match so that the rejects get as less as possible. So let's suppose that the design department specifies tolerance limits TKU and TKL, where the subscripts U and L signify the upper and lower tolerance limit. Also, let sigma j and mu j be the standard deviation and the process mean of the output dimension of the shaft and that is for the jth manufacturing operation or option. So this tolerance limit is as per the kth system of tolerances. And there may be many such systems of tolerances which may need to be incorporated while doing the designing, and so therefore there has to be a variability or there has to be a generic approach saying that a particular tolerance of the kth type is being matched according to the machine capability, where there is a jth manufacturing option being evolved for the kth particular tolerance on a design, okay, or on the design of a certain part. So obviously we'll now have to, because there is a theory associated with normal distribution I'm not getting into because this is something related to more statistical, that you have something called a standard normal variate, okay. And so there will be a variate on the upper tolerance and the lower tolerance, where you're actually measuring the tolerance with respect to the process capability of this particular process, okay. And this standard normal variate Z for the jth manufacturing option on the kth system of tolerances for the upper side comes out to be the tolerance, the upper tolerance minus the mean of the process divided by sigma j. And similarly the standard normal variate for the jth manufacturing process for the kth system of tolerances comes out to be TKL minus mu j by sigma j. So it is really about how many sigma j's or how many standard deviations the tolerance on the upper side is away from the mean, okay. So how many times the sigma j is covering that space between the TKU value somewhere here and the mu j value which is somewhere here. So it is a sort of an impression which calls for whether it is 99% or whether it is 95% or 67%. So if it is 1 sigma j, then probably it is somewhere around 67%. If it is 2 sigma j, it is about 95%. And this comes from common statistics, common mathematics, processes of normal variations and normal distributions. And we assume that you're aware of these normal distributions and how they are handled, okay. So obviously then the if we look at the material balance equations, we have to consider the input, output and scrap units related to the process respectively. Everything should be in terms of cost and then optimization of that cost. So let yjk0, yjko, yjk I and yjks represent the output, input and scrap units respectively. So then at the transformation stage, using the jth machining process, we have the fraction of scrap SCJK as the scrap units per unit the input units. And I would just like to say, or I'd just like to predict this from the normal distribution as shown earlier. So we want to sort of do a material balance equation and try to figure out in terms of rejects. If the reject is higher, obviously the output would be higher, output would be lower in comparison to the input, and the material will be a little bit disbalanced, the flow will be disbalanced because of the rejects or the scraps, and obviously it will be costlier to the manufacturing system and vice versa. So here we want to just indicate what is this scrap fraction that we are generating. That means what is the scrap output in terms of the as a percentage of the input material that is flowing into the process. And then we come back to the so-called normal distribution that we had done earlier. So these z variates that we were showing here, so the standard normal variates are essentially plotted on a table where there is a sort of an area under the curve of the particular z variate into question that is being generated from the normal function. And this area under the curve is quite well tabulated. It is in fact a numerical integral which has to be calculated and put and mentioned in the various values related to that the solution for the normal distribution function. So the normal variate is plotted as a bell-shaped curve, and the area under the curve of this normal variate is also known as the cumulative distribution function, okay, phi. So just putting it this way, that let's say z is the normal variate, and we plot the normal variate as a normal distribution function, and the area under the curve here, let's say if I consider the area up to this particular point, okay, so the area would actually be represented by something called a CDF, or cumulative distribution function. And this CDF is actually a numerical integral which is calculated based on the this normal function right here in terms of the z variate, and it represents the area under the z curve. Okay, so having said that, this also is known as the function phi of the particular z variate in question. So there are two z variates here that we are evaluating. One obviously is zjk lower side. So the normal distribution zjk of the lower side would be nothing but let us say this is somewhere the lower tolerance, and the zjk on the lower side would actually be the total amount of material up to the z lower jk, zljk, the area in fact represented by the circled zone on the normal distribution curve. Okay, and the total amount of area at the upper side corresponding to this curve zujk would be the whole area represented by this bigger circle, okay, all the way up to here. So obviously if we were to consider the scrap fraction, so we can take this directly as the scrap, anything which is in this particular zone below the lower tolerance is rejected. Okay, so we can say that this is phi zjkl, the rejected fraction reject, and we also know that anything above this zone is rejected. And one more thing is that the maximum value of this distribution function happens to be 1. So the area under the curve here, the maximum area under the curve comes out to be 1. So therefore we can say that this part here, right here, which is the fraction reject, being away from the upper value of zjk, okay, zjk is at this particular value, would actually be equal to this 1, the whole area 1 minus the shaded area represented by this big circle here, which is the phi of z ujk. So now it's a case that irrespective of the how many number of inputs, outputs or scrap are being generated, we can simply fit this normal distribution function, which is actually unity, into this domain and create a scrap fraction here, which is represented in terms of the number of scrap units per unit the number of inputs. So having said that now, so the transformation stage would involve even, of course, the simple equation that all the input would either be generated as an output which is successful throughout the manufacturing process, or an unsuccessful output which is a scrap. So this is the material balance equation then we would like to evaluate, and we will take it up next module, how this material balance equation can be converted in terms of costs to a manufacturing system. And then we can also see the time aspect and then optimize a selection decision between the different machines based on whether a process is good, capable, produces rejects or not, so that what is the overall output unit cost. Because of lesser rejects or more rejects, the cost would vary, and vis-a-vis the time, and then we'll try to take selection decisions based on that. So with this I would like to close this particular module. Thank you.